Okay, so we'll begin now. Please let me know if I get disconnected or if the audio is less. We'll figure something out. So we are discussing FDTD models with telegraphers equations. These are the references. So right, we had covered the introductions from DM codes are, and you can study the basics from DK Cheng and introduction to CEM from Matthew and Sadiku. And the contents we'll discuss today will be covered from this particular textbook by David Davidson. Uh, this is this one. Okay, so in the last class we were discussing introduction to CEM and FDTD. So we'll finish with introduction to CEM today, whatever few slides were left, and discuss the introduction to FDTD and start with the modeling of lossy and lossless transmission line. So we'll discuss the modeling of lossless transmission line. Lossy will be homework for uh, the course attendees, that is you guys. You'll have to model the lossy transmission line based on what we discuss in the lossless case. And once we are done with the S parameters in the next class, we will discuss the lumped elements RLC, and using the formulation that we discuss in this class and the formulations we discuss for the lossless case, using these two you can model the lossy transmission line. So I won't be sharing code for the lossy transmission line. I'll share the code for the lossless and these things, and this will be your assignment. We'll see how much we'll be able to cover in the next 2-3 classes, and then if we have time we'll model CRLH, or you can do this once we have covered all these things. So all these things can easily help you model the CRLH transmission lines. So we'll continue from the previous class. We were discussing the CEM modeling process, and the CEM modeling process is the art of acceptable approximation. So we'll be doing approximation at various stages. That first is the mathematical model. Is the first step of model approximation. The second approximation is in the codes. So we will use some approximation in the codes, and yeah, so these are the two steps where we use approximation. Firstly, we are replacing the real world with a mathematical model, as I said. So the first is the mathematical model of the problem. So for example, if you have an antenna and it is radiating, so over there you try to model this physics with some maths. So this is the first model, and then when the real field is modeled using mathematics, then we do some approximations too, so that we can solve this mathematical problem using computers. So let's look at the different things that are involved in the CEM modeling process. First is the first is the limitation of the mathematical model. So while modeling a physical phenomenon, we try, for example, the mathematical models of these electromagnetic devices. They have underlying assumptions. So, for example, we'll consider air or vacuum at places. We'll consider particular sort of charge distribution. For example, while we create mesh, we assume that the current density across a particular mesh is constant, or the charge distribution across inside one mesh is constant. So these are the approximations that we use while doing the mathematical model. One of the first approximation that you see is we are considering lossless case of the transmission line, because we consider that the losses are uh, very less, so losses tend to zero is what we see. For example, R and G will be considered to be zero for the lossless case. So a better approximation is lossy transmission line where we have finite RNG. Tolerances and in any engineered system which has some measured value of tolerance, some of are really little concern and others impact on the device performance. So if we were supposed to do the approximation using electric and magnetic field, in those cases we were using mu and epsilon values, and these are usually complex values, but the initial codes that we usually study, especially the ones which I taught in my previous course, we considered them to be real values. We just ignored the imaginary part until we had to include them. So the imaginary part in those cases refer to the losses again, which are equivalent to the RNG values in this case. And if so again, so if we are not considering the RNG values, this will impact the system. So in case if the particular medium is very lossy, and if we do not use the correct values of RNG or we use some approximation, they might really affect on the performance. So we have to be very careful with the approximations that we are doing. And again, so manufacturing deviations. While if you simulate a particular device, for example, when we are simulating structures inside HFSS or CST, we tend to use PECs. But in those and we when we use PECs, we usually use sheets, and their thickness we assume them to be 0 because they are really thin. But these but this but these can impact the results which we are trying to simulate. So within this tolerance would be the thickness of the PEC, thickness of the conductor. And manufacturing deviations is, for example, if you are using an SMA port with your device, and we usually tend to just use a coax in feed just directly with your antenna structure and not use a SMA. So when we incorporate an SMA into the device, there could be some gaps between the connections, and which could lead to some capacitance values. So these could be manufacturing deviations. And for example, if you're trying to fabricate a device which has very thin lines, and you, for example, if they become unequal at some places, that this could lead to impedance mismatch. So these things come under the manufacturing deviations. And simplifications in the formulation. So again, this is very closely related to the limitations of the mathematical model. When we try to simplify, again, if we try to simplify a problem, we assume the losses to be nearly 0. So these are the simplifications we are trying to do, and the limitations could be if we cannot model the exact values, exact mathematical model. For example, if we have a parallel plate waveguide and we are using a transmission line equivalent, so the transmission line theory is will not be able to uh, correctly, accurately model the parallel plate waveguides. So that could be a limitation of the Telegraphers equations in this case, that we cannot accurately model parallel plate or square waveguides and those stuff. So that could be a limitation of this mathematical model. So the better suited case would be doing a 3D FDTD code which incorporates the entire structure properly. So once we have an acceptable approximate field, then we use the approximate numerical solution for the approximate field problem. So the one of the simplest cases using the central difference scheme, which we'll discuss shortly. We use central difference scheme to model the differential equations. So we'll have this differential equations, but what we do is we use finite differences. For example, fx minus fx x plus delta x minus fx by delta x, some sort of this approximation for this derivative. So the first is the finite discretization, which can cause a problem. So what we are trying to do is, for example, if we are trying to model this particular plate, and so this plate will have some charge distribution over it. But when we try to model them using computational methods, these and we so what we have to do is what we discretize using, for example, if you are using triangular mesh on the surface, in case of FEM or MOM, or using square meshes in FDTD. So these discretization are finite. So since these are finite, there could be some losses. So there could be some error. This could yeah. So there could be some errors if we do not do this discretization properly. And for a better model, what we can do is we can use finer meshes. If we use finer meshes, this will give you better results. But using a finer mesh can cause will require greater memory. So there could be interpolation error, which is if you're solving at different points. So if you use a coarse mesh, for example, if you use just two places, so you'll be solving at these points. And so if you want to find out the current value at this particular point, so what will be doing is you will be interpolating the values of current from here and then calculate the value at the center. So if you so this result can be improved if we use a finer mesh. So so the interpolation error could be reduced, and similarly the mesh dispersion error. So if you use a coarser mesh, there could be some dispersion during the code. So this is something which you will absorb when you start coding, that if you have a smaller delta x, delta y, and delta z value for the fields, then the better is the approximation of the values at different points. And if there is any errors due to these things, they are also contained by the finer mesh. So both the interpolation error and the mesh dispersion error can be controlled by refining the mesh, but unfortunately the computational cost will become very large, and especially if it is a 3D problem. So your mesh, as you increase the density of the mesh, it will require much more RAM and ROM and everything from the computer's aspect. Now, the next problem which we encounter is the finite problem space. So in method of moments, this problem is not like this problem is not there. But for FDTD and FEM, if you have an antenna radiating in the field, but the FEM and and FDTD, they do not have the radiation condition. So you have to terminate the space in which the antenna is radiating. In that case, you're limited by the amount of memory and time in which you want to solve the problem. And for that, we have to choose the best case. For example, if we have a much bigger system, then we can take a much larger box around the antenna so that we can find out the result, and we have larger space. So if you try to solve try to simulate the antenna in a smaller bounding box, so you'll see that you don't get the proper results. You might sometimes also get wrong results. So we are limited by the problem space in which we are trying to solve the antenna, because we are limited in memory. And also in this case, we need to include some absorbing boundary conditions, so that the radiation box does not reflect the fields back into the space. So maybe I try to explain this in a much clearer way. So let's say this is the simulation space you could afford with the memory that you have and the time in which you want to solve the problem. And for example, this is the antenna inside, so it is radiating and we are trying to solve the fields, and at particular distance we are trying to calculate the radiation pattern and gain and other stuff. So and for that we and for example, if you're trying when you do measurements, for example in an anechoic chamber, so they have these cones which will stop the radiation from reflecting back into the space so that we can conduct the measurement properly. So similarly, in this case, we need this radiation boundary condition so that the waves which are emitted by the antenna are not reflected back from the radiation box. And for this we must have our absorbing boundary conditions which should work properly. And so there are different techniques for using the absorbing boundary conditions, and the better boundary condition that you use is the least amount of reflection that you might get. So you'll see later that even if you use the best like the even in theory it shows that there will be zero reflections, but when you try to implement, you'll and if you like to zoom in the magnitude of the electric field or the voltage value which is reflected, you'll see that there is still some reflections because our mathematical model cannot like the codes cannot solve them to that extent. So one of the reasons which I have found out that is that when you're trying to match these conditions, we usually end up using irrational numbers, which when stored in the memory, they so these irrational numbers are infinite. So after the decimal value, they keep going, but we are limited by the memory, and so we use finite number of values after the decimal point. So since these do not match at the boundary conditions, so will be still some reflections, but you can improve them using better absorbing boundary conditions. Then is the numerical approximation. So FEM and MOM, they solve the integral equation problems, and while solving the integral equation problems, they use something called quadrature. Sorry, forgetting the names. Quadrature rule or trapezoidal rule. And what we do in these things is we linearize them. So we try to write them in uh, some values of this particular function, the order. So when we numerically approximate them, so the value which you'll get from these will be very close to the integral value, but they won't be exactly same. So these approximations, if you don't do them properly, or if you don't use a proper function for the approximation, you might end up with the wrong results, or they might have errors which are significant. Now for verification and validation. So if you have written a code to solve this particular solve an antenna, for example, or if you're trying to simulate the propagation of a wave in a transmission line, how do you know that this is correct? So there can be multiple ways to verify your code matches with the theory. So comparison with analytical computed solution is the best what you can do. Is if you solve the problem using your code, and then you solve them analytically using these results, and then verify how much error have you encountered. The next thing you can do is comparison with approximate solutions. For example, this could be a case when, for example, if you have, for example, the interaction of an electric field with this square. So maybe you can analytically solve this, but what happens if this square has some rough edges? So this rough edges, the analytical problem will become very complex. What you can do is simulate the square with rougher edges using your FDTD, for example, and find out the analytical solution for the square, and you will and you can and from your observation you can tell how will the waves be affected by these approximation things. So you can compare the results from a perfect square which you calculated analytically and the rougher square using your code. And if there is some correlation, then you can say that the code is working okay. So this is one way you can try to uh, see. But if, for example, if you're trying to simulate something with this thing and for the rougher square, but you end up with something which is very wrong. For example, if you end up with some infinite values, or if your code is getting stuck, so you'll know that the code is not working okay. The now a better technique for solving a first square, for example, the interaction of wave with rough edges, would be if you verify your FDTD code for the square, and if that is stable, and then increase the roughness, or maybe do- model for example, if it has very like bigger changes across the structure, then what you can do is try increasing the roughness of the square by in steps, and see if the solution does not vary greatly. So this is for this you will be using your intuition as well. The next could be comparison with measurement. So this is a little drastic from these two things, because you have to do this using pen and paper and computer. So once you are satisfied with this, one thing you can do is fabricate your device, measure them in an anechoic chamber, and then see the simulation results match with the measurement results. And if they do, it's all right. If they have correlation, it's all right. But if they do not match, then there's definitely something wrong with the simulation results. And the final one is comparison with other CM codes. So this is usually what we do if you're working, for example, if you're trying to if you are writing your own FDTD codes. So what you can do is you can try to simulate a patch antenna, and the quickest way you can try to verify if your code works is you put them in CST or HFSS and match your results, because you know that these solvers are standard solvers, and they are robust, and they have been tested by their developers, and so they will give you correct results if you have put the correct values given that. So you can verify your code with the standard solvers and see if their code is working fine. So next we'll start with the finite difference time domain method. I'll pause here and take questions that you might have. Okay, so I guess that's all right. So let's start with the finite difference method. So we'll start with a brief history of how this came in. So the FDTD method is a particular finite difference scheme, and it is also known as the Yee's algorithm. So this is Professor KNSC. So he was the person who developed the FDTD scheme, and the FDTD scheme is an explicit marching in time procedure. So this thing will get clear as we proceed with the class. So explicit is implicit and explicit methods, as we'll see in the next slides. Marching in time also will become clear as we see the E grid. To tell briefly, implicit methods require matrices. Explicit method do not require matrices is the first difference. And the explicit methods, the point we are trying to solve the problem can be calculated directly from the previous values and the current values. So for example, if this is the variable you're trying to find out, and you have the values for the nearby points, you can just calculate it directly. While in case of implicit methods, so you prepare your entire matrix, you have your unknowns, and you have the boundary conditions, and then you inverse the matrix, multiply it with the boundary conditions, and you get your unknowns. So this is your unknowns, this is your knowns, this is your knowns, and multiplying the knowns so will give you the unknown value. So this is something what we do in the implicit case, and in the explicit case we just directly solve for each point using the nearby values. Marching in time is as you proceed with time, you find out the value at each location. So for each location, you will, for example, this was your array and this was your value time 1. Then in the next time step for T2, you will update your values, and similarly for each time you will march and you'll calculate the values. So this is an explicit marching in time process that simulates the propagation and interaction of electromagnetic waves. So the method which he developed involved electric and magnetic fields. And this course we are studying its relative using voltage and current. So for at each time instant, the voltage and current values are calculated for each for the entire space. For time 1, we'll calculate the value. Then for time 2, we calculate the entire voltage and current for the entire space. Then at time 3, we'll calculate. So in this way, we are calculating the value at time, and at each time we are calculating the interaction of the, in this case, the voltage and current uh, with the devices that are involved in the simulation space. At present, FDTD is probably the most popular numerical method. So if you are in this field, you'll frequently hear the term somebody is trying to solve some particular problem using FDTD. So the method was first proposed by Yi in 1966. So this method is very old, but for a decade almost until 1980s, it did not become very popular because the boundary conditions were not developed fully when the Yi gave the solution. So when Yi gave the problem, what we did was we would have a source, it would radiate, and we would stop our simulation before the waves were reflected from the boundaries. So when I say reflected from the boundaries, if you try to terminate the space, it would mean you're putting electric field equals 0, or magnetic field equals to 0, which means you either have a PEC or a PMC. And if you have a PEC or PMC, you will experience reflections from the boundaries. So what we would do is we will try to simulate until the time the waves reach the boundary. So this is how it was solved before the boundary conditions were developed. So in 1975, when Taflov and Broadbent, so this is Taflov and this is Broadbent, and Taflov has written the Bible of CEM. So this is a very good textbook. It is also very advanced. So if you, after at the end of this course, maybe you can try reading the text from Taflov. They obtained the correct stability criteria, and in 1981, Moore gave the first stable second order boundary condition. So until Taflov gave the stability criteria and Moore gave the boundary condition, which are very significant achievements in the field of FDTD, the method did not become very popular. So once Moore gave the boundary condition, since then there has been an explosion in the amount of work which is done in FDTD. And then a much better boundary condition was given by Beringer, which we known as the PML, perfectly matched layer. So PML is very important if you're solving 2D and 3D problems. So until 2D, you can use the Moore's boundary condition, but for 3D, I'll recommend you must learn PML and implement them, because the amount of reflections in case of the 3D case is much higher. So the implicit methods and explicit methods. So CM methods can be implicit or explicit. So MOM, FEM, and some kind of FDTD, which usually Yeah, there is something called as unconditionally stable, which we'll not cover in this course, but I'm making you aware that this exists. So there is an unconditionally stable way of writing FDTD codes, which is implicit, and FEM and MOM method, they are implicit methods. And the one which we'll cover in this course, which is the FDTD version using Telegraphers equation, they are explicit. So implicit methods require solution of a set of simultaneous equations, that is, you write x some constant times x plus constant times y. So you'll have your set of linear equations which will, and then you'll separate them into matrices where you'll have all the coefficients over here, your unknowns x y z whatever over here, and then your the values of knowns from the boundary conditions, and then you solve them. So this is how you'll end up with a matrix equation, and then you'll evaluate the unknowns. Usually the matrix is highly sparse, it could be dense as well, and then you you invert this matrix, multiply it with this matrix, and you can end up with your unknown. So this is what an implicit method requires. For your explicit method, the next value at a point is function not only of the current and past values, is and this and the surrounding point, but also the next values of some of these. So for example, if you're trying to update the electric field at this point, so you'll need the values of electric magnetic field from the past points, and electric field value from the past point, and you might also need the electric field values of the nearby points as well. So if you need all of them, in this case, forming a matrix will be difficult, and what you can do is just write the electric field, for example, if at the current time, in terms of the values of electric field past values and magnetic field past values, and just evaluate them as one function and update your electric field values. So this particular scheme where you solve them point by point case is the explicit method. And explicit methods do not require any matrix solution, but they usually require some time step values. We'll get into the Courant limit in detail in maybe the next class, but right now you just remember that we have to maintain the Courant limit. In the previous class we had discussed that it has something to do with t should be less than, sorry, delta space should be less than s by delta x, something of this form. We have to maintain the ratio of time and discretization in time and space, which is given by the Courant limit. So this is something you must follow while writing the explicit method codes. Okay, so before we start with the partial differential equations, any questions from what we covered from the finite difference time domain, introduction, and implicit and explicit methods? Okay, then we'll proceed. So we'll try to quickly cover these points before we start the coding. Um, so these are all some introduction from mathematics. So traditionally, the partial differential equations are classified into elliptic, parabolic, and hyperbolic uh, functions. And so this is a generalized form of the partial differential equation where you will have the dependent values x and y, and they could be in 3 dimensions as well, and you have your coefficients, and based on these coefficient values you find out your discriminant, and these discriminant values give you whether it is, in this partial differential equation, is parabolic, elliptic, or hyperbolic. These come from the conic sections, if you recall. I think I last studied it in engineering mathematics. So if you cut the conic section at different places, you will end up with a hyperbola, ellipse, a circle, or a parabola or something. Yeah, so the way you cut your conic section is uh, uh, is the the expression gives you one of these functions, and these are determined based on the discriminant value that you calculate. So the one of the examples is the one-dimensional wave equation which we use is this is hyperbolic. If you so this is the general form of the wave equation in one dimension, and if you try to evaluate the discriminant, it comes out to be this value which is less than zero, and hence it is hyperbolic. You can try to evaluate this, look at the textbooks as well. You'll get a better idea of how to classify these problems. The book by Sadiko Sadiko, the CM book, and the list of this particular in the starting which we saw, there is a good discussion on these how you solve each of these kind of problems. Now, approximating using finite differences. So this is important because this will be frequently used when you're trying to convert your uh, analytical expression to codes. So depending upon whether the next, previous, or central nodes are involved, one obtains forward, backward, and the central differences. So let us first see this figure, and then we'll see the expressions. So for example, if you're trying to evaluate like the field values, so if you this is you are approximating this particular curve over here, and to approximate, what you can do is pick points. If you pick this particular point and this this particular point, and you calculate the slope. So this particular slope will and this is your true slope, right? The true slope is given by this blue line over here. Okay, so I've covered it with red now. So this will give you an approximation. This, using the central difference scheme, you'll get an approximation of the slope at using these 2 points, and this is the central difference scheme. So what you're trying to do is you take two positions and calculate the central value. But what if you use this particular point and this particular point? So using this, you try to calculate the slope, and in that case, what you do is get the forward difference. I'm correct. So I've made a mess over here. That's all right. So based on which points you pick, as the you get an approximation of the true slope, and this could be forward, backward, or central. So let us look at the expression. So this is your derivative, and your derivative is essentially the slope at that particular point. So if you're trying to solve the slope at the x value, what you and this is how you expand them. So this is the value of your function at x plus delta x at this particular point, and the value at x and divided by delta x, and then you have some more terms, and these come from the Taylor's expansion. So this is how you approximate for the first derivative. You try to find the slope using the finite differences, and this is the forward difference. Similarly, for backward differences, you take this particular value at x, you take the value at the previous point, and then using these you can write the backward difference formula. So you're using these two, so then you get an approximation of the true slope. And the third way is you could take at the two extreme points, and then you can try to approximate the slope at x, and this is the central difference scheme. So all these expressions come from the Taylor's for expansion, and I'll recommend, if you don't recall this, maybe just give it a read. It's not very hard. So these are three ways in which you can approximate your first derivative using forward difference, backward difference, and central difference. To get a better idea, you'll have to try to write this down and then try to absorb it. But once you start coding, this will come naturally to you, especially the central stress formula, which this will be using for our codes. So this is the way we try to approximate the central, backward, and forward difference scheme. These two are not very important from now on. This you have to be very sure that you understand this. Okay, so these come from the Taylor's series, and once you have got your central difference scheme, so this is how your Taylor's expansion looks like. So you write x naught plus delta x, which and these values around the x naught are expanded like this. And similarly, what you can do is you can replace your x plus delta x in the Taylor's expansion by this. So this is the first expression, this is the second expression, and if you subtract these two, you end up with this expression for the central difference scheme. So you have now got the central difference formula. So I'll probably pause over here and let you read this. Maybe you can try using a pen paper and write this down. You'll get a better idea of what math we're trying to do here, or you can do it later as well. So from the Taylor's formula, we write the first expression. From the Taylor's formula, we write the second expression. We subtract these two expressions which we got from the Taylor's formula, and then we end up with this the central difference formula. So once we have got this, we can also find out for the higher derivatives as well. So this is for the first derivative, and for the second derivative, you'll again use the two Taylor's expansions. And I'll leave this as an homework for you how to achieve this. We won't be needing this, but if you solve this, you'll feel more confident about this course. Okay, so once we have the forward, backward, and central difference scheme, let's look at the errors each of them accumulate throughout the simulation. So if you take a look, the forward difference and backward difference, they are dependent upon the second term is dependent upon the delta x by 2, where delta x is the step size in space or time. So this depends upon the delta x by 2 for forward and backward differences, and this is important because what we do is we just use this part of the forward difference and we ignore this, assuming that this won't matter, and since we are ignoring these terms, the error is proportional. So this is the largest value among these two, and the error is therefore proportional to delta x by 2 terms. But in case of central difference scheme, what you see is the term the highest term which we are ignoring is proportional to delta x square by 6 term. So this term is much smaller than the delta x by 2. So the amount of error which we incur in central difference scheme is much smaller than the forward difference. And I'm saying this much smaller because delta x is less than 0. Sorry, less than 1. So delta x is less than 1. And since it is a fractional value, if you keep squaring it, it will become much smaller. Hence the error in forward and backward difference is proportional to the cell length, but for the central difference it is proportional to the square of the cell length. And for the limit, if you are limit delta x tends to 0, the central difference formula will converge more rapidly than the value. So when we talk about creating a mesh, so each mesh has this delta x length, and if you use finer mesh, your central difference scheme will be more accurate than as compared to the forward and backward difference scheme, because if you use finer meshes, the error which will be much smaller is for the central difference scheme. So I'll pause over here, let you read this. Please take a look at these expressions carefully, and if you have any questions, you can ask them now. Okay then. So some technical words: accuracy, consistency, and stability. Stability uh, is stable. So let's start with stability. For a finite difference scheme, the solution is stable only if the errors introduced at any stage remains bounded throughout the entire evolution. For example, if you are trying to solve a problem and if your code is only stable if, for example, if you incur uh, an error at a particular mesh point, and if it does not propagate to all the other points, this you assume that you can say that the problem is stable. But for example, if you encounter an error at this particular node, and if it propagates to all other nodes, it means that your code is not stable. Consistency is when you take a coarser mesh, you obtain some result, and if you keep refining your mesh, and your problem converges, for example, the electric field value you are trying to calculate becomes is consistently uh, converging, then in that case we say that our result is consistent. Accuracy is determined by the numerical solutions. So this is mostly determined if you're using a float value or a double value, and those the amount of better way you are solving the irrational numbers, how much value, whether you're using 5 3.4 or more value. So this is kind of thing which involves your accuracy. uh, it also involves the amount of mesh you're trying to solve. For example, if you're not solving the electric field at this particular point, but you're solving uh, fields near it, and then you can interpolate the value of the field. So how close so this interpolation will depend upon how fine your mesh is, so that will also give you a more accurate result of the electric and magnetic field values at that point. So this is some an example, this is an example of accuracy. So these terms will they are often used by the developers. So you must know. And let's look at the basic solution procedure of FDTD method. So after this we'll start the coding thing. We'll discretize the problem statement and then see the results. But let's look at the general flow of how the problem is solved. So the first step is divide the solution region into a grid of nodes. For example, if you have a 2D problem, then you need to discretize it into space, assign the correct epsilon and mu values, or in this case, since it is a transmission line, we'll discretize it in space and assign the capacitance and inductance values at each node. So the first point is to divide the solution space. Uh, Approximate the derivatives of given partial differential equations by the finite differences. This is what we'll see in the next slide. For example, we have dv by dt related to di by dx, and di by dt related to dv by dx. So this is how the telegraphers equations look like in this case. Or if you have your electric fields related to magnetic fields. So the next step is you have to use finite difference of electric field at different points, discretize them, and so this form you'll discretize each of these values and then get the approximate expression for the Maxwell's equations or the telegrapher's equations. And then once you have divided your space and discretized your equations, then you try to solve the finite difference problem subject to the boundary and initial conditions. For example, once you have the simulation space, you have how you will solve the electric and magnetic field values or voltage and current values. Then you must use the proper boundary conditions, and for example, if you have a source, then you introduce the source based on your initial conditions. So if operating in the time domain, this amounts to finding the values at the next time step, and this process is variously called time marching or leapfrogging. So leapfrogging is why, because we find out the electric field value over here, then we find out the magnetic field values over here, and then we jump to the next value of electric field over here. So this is also known as leapfrogging or time marching, because we march in time t1 and then t2 and t3, and in between also we have t1.5 and t2.5. So we are marching in time, or we are leap jumping between points, so we call it time marching or leapfrogging. So I'll pause over here if you have any questions. Okay. So let's look at the problem statement. So this is the FDTD solution of one-dimensional lossless transmission line. So in the first class, we had seen the unit cell for the transmission line for a delta z region. So this particular delta z is a discretization of a long transmission line. For example, this is your transmission line, and from this transmission line we take this particular delta z section and then enlarge it, and we're calling this lossless because we have ignored the resistance and inductance values which were in series and shunt. So since R and G tend to 0, in this case we have the lossless transmission line unit cell. Now for this lossless transmission line unit cell, uh, this L and C, as we have seen, as the inductance per unit length and capacitance per unit length. Focus on the per unit length part, must remember. And the voltage across these are given by the Telegraphers equation. So we have seen in the previous classes that we can derive the Telegraphers equation for this particular unit cell, and since we do not have R and G values, the Telegraphers equation for a lossless transmission line becomes as simple as this. And it should be noted that these are a special case of Maxwell's equation. So whatever things we are trying to solve using current and voltage over here can be also applied for magnetic and electric fields. Uh, the first transmission line problem that we'll be solving will involve a generator, source resistance, your transmission line, which will have an impedance maybe Z0, and we'll have a load resistance. So let's discuss the analytical solution first, and it will be your assignment to verify your analytical, like write the code for the analytical solution and match it with FDTD once we have done a couple of more classes. So if you have LNC as 1 Henry per meter, 1 farad per meter, the total length of the transmission is 0.25 meters. Your RS and RL are 1 and 2. So this is kind of an normalized problem. So what we usually did using Smith chart, if you recall. So this is a normalized problem, and for this normalized problem, the model and we can take this particular source over here. So by using these values you can calculate the wave propagation velocity and everything, and so you'll end up with this particular source. You can put the source, and for this case your boundary conditions will be this. So if you solve KVL and KCL value equations, you have a source over here, you have so voltage at this particular node and V 0 will be given as the voltage due to your source, and the voltage drop due to the source resistance, and similarly the voltage at this particular node will be equal to the voltage across the load resistance. And you can take the initial conditions as the voltage V over here and current over here to be throughout this value to be 0. So the transmission line initially has 0 voltage and current. You have just attached your generator, and you have load and source resistances. So the solution, exact solution, if you solve the wave equation, will be given by something like this, and you will have your this V plus value and your reflection coefficient values and your propagation constant value. So this is the analytical solution. You can write your MATLAB codes by yourself. Since this is a CM course, I won't be teaching you this, but once you have done this, you can verify what we do with FDTD. So let's start the solution for the FDTD problem. So this is your E grid. So earlier we discussed what is a E grid. So this is the E grid, where this is your simulation space, and we have labeled each node, and at each O we are trying to solve the voltage, and each plus we are trying to solve the current. So we will evaluate uh, electric fields over here, and then we will evaluate uh, magnetic fields in between these two values, but also at a time offset, so which will evaluate the magnetic field, the current values over here. And similarly, in the next time, we'll again evaluate the electric fields in between the so we'll evaluate the voltage values in between the current values, but at a half time step. So why half step? Because we're trying to approximate. We use the previous voltage value and the current voltage value to get the value of the current in between these two steps. So that we can satisfy the central difference scheme. So before we discretize the Telegraphers equations, let's first define the delta Z and delta T terms. So each node will be referred to by ZK. For example, if you are referring to the kth node, if this is the kth node, the kth node corresponds to k minus 1 into delta Z. So for example, if this is the kth node, we will this will be 1, this is 2, 3, 4, 5, 6. So, and since this is 0, and so this is 6 minus 0 into delta Z, and this will give you the length which you have covered. So this determines the Z distance and how it is related to the discretization in space. And this delta Z value can be calculated by the total length of the transmission line, which was h, divided by the total number of points minus 1 which you are taking. Similarly, for time also, each time the time instant can be calculated approximated as n minus 1 into delta t, which is the discretization in time, and the delta t can be calculated by the total time for which you are simulating a problem, divided by the number of time instants for which you will run your code, and minus 1. Don't stress about this. You'll get this when you write the code. So uh, this is simply the discretization. For example, if you want to reach this node, how do you refer to this particular point? So you calculate the number of points and divide it by the number of points and the length of each distance between each point, and you can reach that particular position. Similarly, for each time instant, you calculate a delta t, and for each delta t you will iterate the code. So for example, at the first time, for the first time instant, it will be delta t, and the second time instant it will be 2 delta t, third time instant it will be 3 delta t. That's what we are trying to do over here. So t1, t2, t3 is calculated like this. And since we are also evaluating the current values in between the voltage values, we will also have half time points and space points, which can be calculated like this. So these are something to discretize your simulation space, and you can refer to each node or in space and time by these values. And since we also have to implement the boundary conditions, and your simulation space starts from this particular point and ends over here. But once on the next slides, we'll see that to calculate the value of electric field and magnetic field at these points, you will need the value of the previous time instant as well, and the next time instant as well. And for that case, we define the uh, electric field and magnetic field values in you don't have to do this in code, but for writing the code, no, to do the formulation, you will need to discretize it. Just give me a second. Yeah, sorry about that. So since we have seen that in explicit time, in explicit methods, we evaluate the electric field or magnetic field or voltage and current values based on the previous values and the next values. So for example, if you're trying to solve at the 0th position, you will need the value at minus half value. For example, if you're trying to evaluate for the voltage values, you will need the current values at minus half time. So right now we will discretize this point as well, and later we will try to evaluate these values mathematically and try to eliminate the need to calculate these inside the code. But for now, we will also discretize one unit cell outside the simulation space and the simulation time. Okay, so let's start with the discretization of the first Telegraphers equation, the first equation, Telegraphers equation, which is the derivative of current in terms of space, which equals the capacitance per unit length multiplied by the derivative of voltage in time. So for the first term, this is the expression. So what we do is we are discretizing the current with space, and since we discretize the current values at half time instant, so this, and since this is at the kth node and at nth n plus half time instant, so and this we are doing this in space, so the time remains constant. So this is your n plus half, n plus half remains same, and this is at the kth instant, so this becomes k plus half and this becomes k minus half, and this is, and the distance between the two nodes is delta z. So we have discretized the current in space, and similarly for voltage, since we are discretizing this in time, and this is at kth position and n plus half instant, and we are discretizing in time, so the k remains same over here, and this is n plus half, so this becomes n plus 1, and this becomes n, and this is delta t by delta divided by delta t, because the difference between these two instants is delta t. So this is very important. I'll give you let you read this, and if you have any questions, please ask. This is very important. Okay, so once we have got these discretize these two derivatives, what we can do is substitute these back over here and then evaluate. And once we have done that, we will get an expression like this. So maybe what I can do is try writing this for you. So this is I n plus half k plus half minus I n plus half k minus half by delta z equals minus c v k plus 1 minus v k n divided by delta t. So once what I've done is I've put these values over in these two at these two positions, and now what we do is we look for the latest value. So the latest value over here is v n plus 1. So all the time instants, for example n or n plus half, come come before the n plus 1 time. So if we are marching in time, and this is we are marching in time, and this is n equals to 0, n equals to 1, n equals to 2, n equals to 3, and in between we have n equal to half, n equal to 3 by 2, n equal to 5 by 2. So this is what, this is n, this is n plus 1, this is n plus 2, n plus 3. So n plus 1 comes before n and n plus half. So this is n plus 1 is the latest value, and we will try to separate the latest value from the previous values. And if you try to evaluate, what the first step is, will will bring in these on the left hand side. So this will be minus c. Uh, so this will be delta z, t minus delta t divided by uh, c delta z into I n plus half k plus half minus I n plus half k minus half, and this is equals to vk n plus 1 minus vk n. And then we bring this term on the right hand side, and we end up with vk n plus 1, which is the latest voltage value, the latest value of voltage, which given in terms of the previous value of voltage, the coefficients, and the previous value of currents. So k n plus half and n plus half are the previous current values, and nearby points, and this is at the voltage value at the same point. So if you look at this particular stencil, this was the voltage value that we were trying to evaluate. Okay, and this was the volt. So zeros are the voltage values. Zeros are the voltage values, and currents are given by the plus. And this is your nth instant. This is your n plus half instant, and this is your n plus 1 instant. So this is your n plus 1 instant, and this is your n plus half instant, and this is your n instant, and this is your kth position. So this is your kth position, this is your k plus 1 position, this is your k plus 1 position, and this is your k plus half position. So what we can see is that the voltage value at the kth position at the latest value, which is this value, is given in terms of voltage value at the kth position from the previous time instant. So from the previous time instant, which is this value, so this value is used, and then current values from the nearby point at k plus half and k minus half. So this is k minus half current value, and this is k plus half current values at the n plus half instant. So at the n plus half instant. So these three values are used to evaluate the latest value in voltage. So this is your voltage stencil, and this stencil will be used to evaluate at any point. For example, if you're trying to evaluate at this particular voltage values, then for this particular voltage value, you'll need this particular current value, this particular current value, and this particular voltage value. If you just move the stencil. Similarly, if you are trying to evaluate the voltage value over here, you will need the current values over here, current values over here, and the voltage value at the previous point. And from these things, you can just calculate the voltage value. So this is your voltage stencil, very important. I'll pause over here, let you read this. Let me know if you have any issues with this. Okay, so if there are no questions, we'll proceed. We'll do a similar treatment for finding out the current values as well. Okay, so similarly, will use the second transmission line equations, and so this is your voltage discretized in space. So, so since we are trying to evaluate the voltage at k plus, okay, we're trying to evaluate the voltage at k plus half position. Yeah, so this is the k plus half position, and so for the k plus half position, we'll use the voltage values at k plus 1 and k. So you must remember that voltage is evaluated at values like k minus 2, k minus 1, k plus 1. So this is evaluated at the integer values traditionally, and for the currents, we usually evaluate them at halves, k minus half, k plus half, k plus 3 by 2, or k minus 3 by 2. So current usually we evaluate the current values at the fractions, and the at the complete numbers we evaluate the voltage. So we are using k plus 1 and k over here at the same time instant, because we this discretization is in space, so the time remain constant and the voltage of nearby nodes are used. And similarly, when we discretize the current, we use the since and this is discretized in time, so we use at nth instant we are trying to do this. So this is n plus half and n minus half, and the node remains constant, and this again is at a fractional value. So this is how we discretize the voltage in space and current in time, and then again we put them back. And if when you put them back and try to evaluate, so you will notice that in this case the latest time instant is n plus half, because the voltage are given at nth instant and the current is given at n plus half and n minus half. So n plus half is the latest current value. We'll try to bring this to the left hand side and all the rest of the values to the right hand side, and once we have done that, we'll get the current value at the latest time instant at the k plus half position, in terms of the current value at the previous time instant at the same position, and the voltage value at the previous time instance and the nearby points. So similarly, if you look at the current stencil, we're trying to evaluate the current value over here, and the current value is given in terms of the previous current value at the same point. So we're trying to evaluate this at k plus half, and at the k plus half location, this was the current value at n minus half, and this we're trying to find out the current value at the n plus half time, and it is also given in terms of the voltage values at nth position, nth time instant, and k plus 1 and k position. So this is the k plus 1 position, the voltage at the k plus 1 position at the nth time, and kth position at the nth time, and current value at the n minus half time at the same location. And using these three values, you can calculate the current value at this particular point. And you can move this stencil anywhere. For example, if you're trying to find out the if you have to find out the current value at k plus, okay, k plus this is k plus, this is k, this is k plus 1, this is k plus 2, this is k plus 3 by 2, right? Yeah, so this is k plus 3 by 2 to th position. If you want to calculate at this particular point, you will need the current voltage values at these two nodes and the current value at the same node at the previous time instant. And using these points, you can calculate the current values over here. Similarly, if you want to calculate this, you will need the values from these points over here. And so since this is marching in time, so this is the time axis, we are increasing in time over here, and this is the z axis, and so we are increasing in space over here. So the latest value of current is dependent upon the previous values of voltage and the previous value of current itself at the same position. So this is the current stencil. This is very similar treatment to what we did in the previous slide. I'll again pause over here, let you read them, compare them, and if you have any questions, or if I'm emphasizing that the previous two slide and the previous slide and this slide, these are very important. So you must understand this. If you do not follow this right now over here, maybe come back, rewatch this lecture, read the David B. Davidson book, or try with the electric field and magnetic field values from DM Sullivan. So you can try these things, but you must understand what the mechanism in the way which we are discretizing the equations and discretizing the space. Very important. Okay, so now that we have formed the stencil for voltage and current values throughout the space, the only problem lies when we are trying to evaluate at them at the boundary. So for example, if what happens if this is n equals to 0, or this is k equals to 0. So if we are trying to evaluate them at k equal to 0, the stencil tells us that we will need the values at k equal to -1 or n equal to -1 values will be needed, but we do not have the information for negative so t equal to 0 essentially means when we are trying to simulate from when we are trying to simulate the time instant. But if we're trying to simulate from t equal to 0, we won't have any information of t equal to -1. And similarly, n minus 1 and capital N, for example, +1, as which they lie outside the simulation space. Again, we don't have information at those points. So by using the boundary conditions, we'll try to eliminate the need to calculate voltage and current values at these points. So these are the boundary conditions that we had discussed before starting the simulation problem. So the first boundary condition was at the generator, which meant that voltage at the between the start of the transmission line is equals to the voltage by the generator minus the source resistance, and similarly voltage at the second boundary is equals to the potential difference with potential across the load resistance. And the initial conditions told us that the voltage and current were 0 throughout the transmission line. Now using this, we obtained in the previous slide this expression, and using the boundary conditions we can write for the boundaries we can write this expression over here. But the problem is we do not have this value over here, and similarly we do not have this value over here. So we need to evaluate these two conditions, and for these two what we can do is the first boundary condition tells us this expression, and so the voltage at t yeah, so the at any instant this voltage will be equals to V1 at any at the first node, and we can discretize this current value over here in this fashion. So the discretized boundary, so we are discretizing this and we are using this expression over here. So from this we get the discretized boundary value, and what we do is, since we do not have this time this particular value, we try to we bring this on the left hand side, and this is the unknown in this case, and we try to write all the knowns in terms of the unknown value. So we did not have this value of current, so now we can give the current at the half value, so as we try to simulate t from t equal to 1. But and hence we do not have the value of t half. So we are giving we're trying to simulate from z equals to 1 for current, and we do not have the value of z equals to half for the current. So we are giving the z value of current at half position in terms of the uh, 3 by 2 value of the current, and at the 3 by 2 node, and the voltage at the nearby points. So this is the first boundary condition that we have achieved. So now we have got the one unknown which was over here. Now, and using the second boundary condition, which is voltage across this load, we can give the voltage across this load as this expression upon discretizing, and the current as at this particular node in terms of the previous current value over here and current value over here. Upon discretizing, and then after discretizing this expression over here, we we get the value of current and at the later position in terms of the previous current values and the voltage value across the load. And once we have got, yeah, the and this current value over here, we can substitute this back into the previous expression. So we did not have this unknown, this was unknown and this was the unknown. In the previous slide we evaluated current at half value, and we in this slide we evaluated current at the uh, n plus half value. We'll substitute them, and upon substitution we get the voltage values at the boundaries. So the voltage value at the boundaries are given in terms of the source resistance and the source voltage, and at the low at the second boundary, which is at the load, is given in terms of the load resistance. I'll share the slides at the end of this class, and then you can try to work out the maths from here. So this, just give me a second. Yeah, sorry about that. So this is the first boundary condition slide. So where we try to evaluate the current value at the half node, because the current value, uh, this is the first node, right? So we do not have the value of current at the half node. So we try to evaluate this, and the next, and we had got the expression for current. Similarly, in the previous slide, and the next slide, we evaluated the current value at this node over here after the simulation space. Once we got the values expression for the current values, we substituted them back into the update equations, and these are the boundary conditions. So try to work out these the maths in this scheme then for the boundary conditions by yourself. And now we have got the boundary conditions for the voltage, and similarly, so one thing is that we can notice is that we still need the value of the current value over here, the voltage value over here, and this is our source. So this is already known. So this you can put anything you want. Just because this is your source, you can put a sine wave or a cosine wave or Gaussian pulse or anything. So this is known to you. But what about when you'll start running your code, you will need the voltage and current values at these points. So from the initial conditions, we can say that all of these values were zero. So you just substitute zeros And these values, you can read the slides, and that's all the slides say. Yeah, so we put them 0 all these instants, and in the first run, and you just give your simulation, you give your excitation at this particular point. These are the boundary conditions, and in the first and when we discretize the problem, we had got the update equations for throughout the simulation space. So in summary, your voltage and current values in the beginning of the scheme will be 0 for all the points, and then um, for greater for after your first value, first iteration, these are your update equations. So for v equals to 1, which is your, this is your simulation space at t equals to first, and for sorry, n equals to 1, everything is 0 except your excitation point, for example, which could be anywhere or at the start. So you give an excitation at t equals to 1, which is n equals to 1. And then for the next iteration, what you do is you solve for the voltage using this expression at the first node. At the first position, you evaluate using this, and then for all the nodes from here to here, you evaluate the voltage using this expression. So this is, if this is 1, you solve 1, and if this is 2, then for this entire space you use 2, and then for voltage value at 3 is given by this expression at the last node. And this is the expression, updated expression for current, which remains same throughout this. So your boundary conditions are essentially so sorry, this is your boundary condition and this is your boundary condition, but the boundary condition is only applied on the voltage values, and the current will automatically take that into the account. And this is your expression, update expression for the voltage inside the simulation space, and this is your for update equation for current inside the simulation space. So essentially what happened, what we did was we calculated voltage value over here and voltage value over here, and then we calculate the current values and voltage values inside the simulation space. So the boundary conditions are only applied on the voltage values, and we will essentially solve for one less current value. So we just skip this current value so that we terminate the space over here. And to for the since, and you, as you see, we have some n minus half values or k minus half values going on. For simplicity, what we do when we write the code, we just write n plus half as n, but you don't but please do not confuse uh, n plus half to be same as n. We're just writing them because inside, when you write arrays or vectors inside MATLAB or in C, you need whole numbers. You cannot give them fractions. So we use whole numbers, and then hence we are using we approximate. We just write down n plus half as n. So we are evaluating voltage at 1, 2, 3, 4, and so on, and current at 1.5, 2.5, and 3.5. But inside the code, it will look like we're evaluating current at 1, 1, 2, 3, 4. But do not confuse them that we are calculating them at the same position or same time. They have an offset. So this must always be kept in mind that they are not the same, and they are not being evaluated at the same position. It's just that we are inside the arrays and vectors, we are using the same indices. So I'll pause over here. Please read this. If you have any questions, you can ask them. You can also come back for questions in the next class, because we covered a lot this time. And the next slides will uh, see the codes, simulation results, and the codes which we wrote down for the set of equations. So I'll just quickly summarize the steps which we did. We discretized the space, then we discretized these equations, that is we used central difference scheme on partial differential equations, which was the Telegraphers equations. And then we wrote down the boundary conditions and the initial conditions. We discretized them using the central difference scheme on boundary conditions and initial conditions. We got rid of I value at half and I value at n plus half. And when we discretized these, we got update equation inside simulation space. When we got rid of, we got update equations and boundaries. So this is what we did in short. Now once doing that, we got the initial values, got the boundary conditions, and the update equations for voltage and current. Now let's look at the simulation results, and then we'll see how we did the coding. So the first plot is when there's a transmission line. The transmission line has a 50 ohm characteristics impedance. There's a source which has a 50 ohm load, and there is 50 ohm source resistance, and there's a load which is also 50 ohm. And then so in this case, and then we are using a Gaussian pulse. The Gaussian pulse looks like this. So this Gaussian excitation should transmit from this particular node. It will travel from throughout the transmission line, and since the load is matched to the transmission line, the reflection coefficient is equals to 0, so there will be no reflection from the load. Let's play and look at that. So this is your Gaussian pulse. Can I forward it? Yeah. So okay, so you can see this travels to the boundary, and since the load is matched, there is no reflection. But in the plot 2, we change the load impedance to 100 ohms, and over here you can see the Gaussian pulse. Okay, is this not playing? Yeah. So there's this Gaussian pulse. It moves forward, and you can see there's some reflection because the load is not matched, and goes back. So in this case, the RS is matched to the characteristic impedance, but it is not matched to the load resistance. In this case, the source resistance is matched to the load characteristic impedance, and that is matched to the load resistance. In plot 3, we have the same criteria, but we are using a sinusoidal source. So for a sinusoidal source, you will see that since it is matched, there is no reflection from the second at this boundary. But if it is again, if it is not matched, you will see that after some point you can see the standing wave happening. So as there is the forward wave and there is a backward wave which are interacting in the simulation space. So these are the results which you can simulate with the code which we'll discuss now, and which is based on all the discussions that we did in the previous slides. So all the simulation can be easily can be done with the discussion that we have done so far. Okay, so we'll start with the code. Before that, does anyone have any questions? Because we'll discuss the code now, and we'll have some discuss your next assignment, and we'll end the class. So, any questions so far from whatever we covered before we start the code? Okay, so I guess not. If you have any questions, we can discuss them in the next class.
Just a question, Prof.
Yes, Benjamin.
You are discussing the case on the boundary conditions where you've got a perfectly matched layer like a PML. What happens in a case where you don't have a PML, or maybe you've got a PEC material? Because sometimes when we do simulations with antennas, sometimes you are using PEC and sometimes you are using PML.
Okay. So in that, so your question is what happens if we have PC or PMC instead of a matched layer, right?
Yes.
Okay,
On
so
the bounding
okay,
box.
on the boundaries. So in case of PEC, what you can do is you can, for example, for PC. So, and if you're writing your FDTD code on the basis of electric field or and magnetic fields, so in that case, you can force your electric field to be zero at that boundary, and that will replicate the PEC condition. And if it is a PMC, you can force your magnetic field to be zero at that boundary, and it will enforce a PMC boundary condition. And for in this case, when you're using Telegraphers equations, what you can do is you can make your voltage zero, and that will enforce a PEC. And if for a PMC, you can force your current to be zero at that boundary, and that will implement a perfectly matched perfect magnetic conductor if you make your current zero. So that is how you can implement PEC or PMC in the FDTD space by enforcing these conditions. And this is very straightforward actually. When you write your code, you just put these values equals to zero, and automatically the other the fields are updated and forcing these boundary conditions. It is much more difficult to implement, for example, what we did just now, implementing a load impedance, for example, a Z value or a complex load. That is much more complex as compared to implementing a PEC or a PMC. I hope I was able to answer. Do you have any follow-up questions on this?
No, thanks, Prof. Yeah, that answered it.
Okay, so so up till now we have discretized the voltage and current equations inside simulation space. We have seen how to implement source excitation at one boundary and match and use a load resistance on the other boundary. So we'll start with the code and before we encounter the update equations, we'll first need to set the simulation space. And this codes has the code has been, which will discuss now, is written in MATLAB. So if you're using anything else, you might have to change your code accordingly. The syntax or the functions which are not available probably in C or Python, you might have to write them yourself or use a MATLAB library to get those. Up till now, one thing which we have not discussed is courant stability criteria, which we have enforced in this we have used in this code. But again, we'll just assume for now that we know this and then discuss it later. So it will become much easier if you try to run the code with different stability conditions and see what happens. So that is one way to better understand how factors affect. So the first statement is something which we do in MATLAB. So let's just skip it. So the clear all, close all, and CLC are basically used to clear the MATLAB screens. And clear all removes all the variables which are there in your simulation space, so that you start afresh. Close all closes all the figures and open windows, and CLC clears your command area. So this is MATLAB stuff. Now Fmax is so this is how I write the code. This is not the way. This is not like uh, any strict criteria of how you write the code. This is how I have written this code. So I usually prefer to assign the maximum frequency up to which the FDTD code will be handling the frequencies, and up to which frequency it should be stable. So I have decided that let's keep this as 30 gigahertz, and then we have assigned the C variable as the speed of light in vacuum, and then using, okay, I think I've misplaced this particular variable over here. So this FOP should have been over here, and the operating frequency for this particular case is 2.45 gigahertz, which should, I think I misplaced this. So it should be over here. And FOP is basically the operating frequency on the basis of which I'm calculating lambda, the wavelength, and based on this wavelength, I'm calculating the length of this transmission line. So I've used a very indirect way of calculating the length of the transmission line. You could just directly put this L naught equals to 1 meter, and you that's it. You don't actually have to do all of this, but I have written it in a way that I have chosen a frequency, and then based on this frequency, I'm calculating the wavelength, and I want the length of the transmission line to be lambda by 2 at this particular frequency. So that's how I have written it. So I've chosen a frequency. I've chosen a frequency FOP, which should be 2.45 over here. Then using the FOP, I've calculated the length, wavelength, and based I've kept the, okay, so I've kept this as 2 lambda, so length of the transmission line. So I've got the length of the transmission line as L naught, which is 2 lambda based on the operating frequency 2.45 gigahertz. The next step is discretization. So based on this Fmax, the frequency until this should be stable, I'm calculating the delta Z value. So this delta Z is equals to C by this C by the total length of the total dimension, which I'm calculating as 10 times F max. So yeah, so okay, I probably have to write this down. So for F max, we will have a corresponding lambda, and that and what we had discussed that we usually tend to keep discretization as lambda by 10, and for that, so this delta Z is calculated as C by a particular lambda 1, and this particular lambda 1 is actually, if you calculate, this will come as 10 F max. Okay, I'm doing something mistake over here. Just give me a second to figure out because what I wrote.
Actually, you wrote lambda by 10 as lambda you wrote in terms of C by F max. That's it. Same lambda by 10 only you wrote there.
Yeah, if
Lambda
you are
you,
if
yes,
you're able
lambda
to
you
follow
wrote,
this.
yes, you wrote lambda as C by F max.
Yeah, yeah, that's it. Yeah, correct. So I've written C lambda in terms of C by F max, uh, and if and this has and since we are taking this as lambda, we usually approximate by lambda by 10, so this becomes 10 F max. Yeah, so we're calculating this delta Z value over here. And then once we have got the delta z over here, they can discretize this whole simulation space. We can count the number of nodes that we have to calculate by just the total length of the transmission line divided by the delta uh, z value. So we get the number of nodes that we have to solve for. And for now, let's just assume that the Courant stability factor is correct, and we have got this S scale value which will multiply with the time step. So we are calculating the time step delta t is equals to Courant stability factor multiplied by the delta z value divided by c. So this is you just for now we assume that this is known to us. We'll discuss this in detail in the next class. So this is how we calculate the time step. So we got the time step. So up till now we have decided a particular maximum frequency for which the code should work, and the frequency at which we use the frequency to calculate the wavelength, for which using that we calculated the length of the transmission line. So we have got the length of the transmission line. We have discretized the transmission line by using delta z, and we got the final node value by as zdm, z and dim, and we have calculated the time step value using the Courant stability factor, Courant stability criteria. Now about the source, you can use either a Gaussian pulse or a sinusoidal source, which could be so if for the sinusoidal source I have just kept it as 2.45. If you are using Gaussian pulse, you can either write them in terms of your you can write them in terms of the time values in seconds, or over here I have just used some random values which I thought would look good, look good in the simulation, which is t naught and spread value. So this t naught is the delay after which the Gaussian pulse starts, and the spread value is how big your Gaussian pulse is. So this, if you increase the spread, your code will have a more flatter Gaussian pulse. So that's it. So you can study these. So these are very simple stuff which are not relevant to FDTD, but yeah, so these are your source specifications. Now we need to calculate the total number of time for which this particular code will run. The total time I've calculated it in this way, in this fashion, that this is your total simulation space, right? So this is your total simulation space uh, over here. So, and for a wave to travel from the first node to the last node can be calculated in this way. The total length divided by this speed of light over here. So this is the total time this particular wave will take from the one to first from the source to the load, and then to calculate the total time step, I've used the total time, got the total time divided by the uh, time step. So I've got the total number of time steps which it will take to reach from one end to the other. Then I have multiplied by 3 so that I have enough buffer that I can see the reflected wave from at both at both the ends, and then added some padding for the Gaussian pulse, just if for the delay. You can, or simply just use some like 1800 steps, or like just write 5000 steps, and that can also work. I have like overthought this thing. You can just put the t steps value and go ahead with the simulation for your initial time, and later you can also use some expression to determine how much time your code will need to simulate. I was once told that we should simulate at least 15 times the total thing. For example, if you have a wave traveling from one end to the other, simulate it for 15 times or at least 10 times like this. So the wave you have seen all the reflections before performing FFT on your code. So this was I was told in one of the classes. So if you want to follow that instruction as well. Um, So I'll let you read the code if I've already written a lot on the code, but if you want to see, take a look. I'll just pause over here. Um, I'll take any questions if you have from this. Okay, then we'll proceed. So we have 3 more slides to go to complete the code, but not a lot of the equations will actually matter for you. Let us just quickly do this slide so that in the next slide we'll see the update equations. So we have initialized all the variables. The next step is to write down the voltage and current matrices. And since this is a one-dimensional case, it is just an array, or you can call it vector. We are defining the voltage and current values at all the points. Since we know that the first node is 1 and the last node is ZDIM, so we have defined the voltage and current values at all the nodes to be 0 as the initial conditions. Now for the boundary conditions, we have put the value of the source resistance and the load resistance as 50, 100. You can vary them. Now for the transmission line specs, we are choosing the characteristics impedance to be 50 ohms, and we're we over here we are taking the value the speed of the wave to be equal to the speed of light, and hence we can evaluate the impedance and capacitance value for this uh, 50 ohm transmission line. Now, alternatively, you can directly put the impedance and capacitance value by yourself in Henry. Make sure that, for example, if you want it to be 1 nano Henry, just put this as 1 e minus 9 and you're good to go. Similarly, if you want to be 1 picofarad, just write it as 1 e minus 12, and you can just put direct values of inductance capacitance, um, or you can do it like this: put choose an impedance value, choose the speed wave propagation velocity, and then evaluate like calculate the impedance current values. Once you have got the current and inductance value for the transmission line, you have to store it at all the nodes. Since you are discretizing them at each node, we create an array of capacitance and inductance, and for each node we update the LNC value. So now we have stored the LNC value at each node, and we have defined vectors for calculating current and voltage at each node. To simplify the next steps, what I have done is I have renamed beta is equals to delta t by c delta z, which is the coefficient which is usually encountered like for each step. So you can directly write this inside the code as well, but I have written like this: delta t by c L delta z as gamma. So this is the coefficient which was used in Telegraphers equation when we used the update equations. So we had V is equals to V Vn plus 1 in terms of V minus delta t by c delta z times current minus current value. So this was something. So we had some coefficients, right? So what I have done is evaluated them before running the code so that the code becomes faster. So we are evaluating beta and gamma. Let's just skip this. This is for the generating the moving plots. So you can I'll provide this in the code so that if you want to reuse this, you can also comment this while running your code. So from here is the actual FDTD codes which start. So we are running this for all the time steps. So as we said, it is a time marching process. So at t equals to uh, at t equal to 1 value, we'll calculate the voltage and current values at all the position. Then we'll again calculate the current and voltage value at all the time steps. So there's an outer for loop. Uh, this, uh, I've used three different types of excitations. So first was the Gaussian pulse. The next is a Gaussian modulated sine modulated Gaussian pulse, which will have a Gaussian envelope, and the third was a sinusoidal pulse. So three options will be available in the code, which will share. And then once you have chosen the type of excitation, I'm storing them in this pulse value, and then I'm using the pulse to update this voltage value, V naught value, and this V naught also I'm storing it, so that later if I want to see this its spectrum, I can perform an FFT and see the spectrum of the source which I've given. Now this is the first boundary condition at the generator. This expression at the line 61, line 60. So the first node is written in terms of as 1 minus delta, what was the expression, delta t by c delta z, delta t by c delta z uh, into rs, and this whole thing is multiplied with uh, vz naught, and then similarly 2 times delta t by c delta z, and then the current value at for the first instant, and plus 2 delta t by c delta z rs and v naught value. So this is there might be some errors in which I'm writing the expression, but the first boundary condition that we have written is written over here. And then so we using this we have initialized, we have updated the voltage at the first node, and for the second node to the last the node before the last node, will we update them using this for loop. So we are starting from the second node and we'll run till the second last node, and this is the expression for voltage in terms of the previous voltage and the coefficient and the previous current values. Note that we are reusing the same variable over here. So since we have already this was the previous value, and we will update the new value in the same variable, so that we are using just two arrays over here. If you want to keep the previous values as well, then you might need to create like v new and v old, and I new and I old, some keep two variables, and then you can keep older values as well. What we generally do is we reuse the same variable and update the latest value to the same variable. So we have updated the voltage values throughout the field, throughout the simulation space, and at the last boundary at ZDIM, we are using the second boundary condition, where if you can like if you go back to the slides and you can see the analytical expression that we derived, sorry, the finite difference expression that we derived. So over here now this is using ZL values, and this is how we have terminated these last voltage boundaries. So these are your voltage values, and once you have updated all the voltage values, you can use you will just update your current values again using the using a loop. So for each values you can also vectorize this if you know a bit or two about MATLAB or Python, but I find it simpler to write the loops. So gamma is the your coefficient that delta t by L delta z value something,
Yeah.
and in terms of the older v values and the current values. So this is how you update the current values. So over here we have used all the update expressions and the source excitation. Um, so I'll just pause over here, let you read this. It will I think it should have been better if I would have kept the analytical expressions next to them. Okay, maybe in the next class I'll do that and go through the code again. Do you have any questions on this?
Yes, Prof.
I see some noise. Yeah.
Yes, Prof. So for the vectorization instead of the for loops, what you are meaning is that that for loop can be unrolled and can be performed in parallel. There's no need for one to do one by one calculation so that we can calculate this faster if, let's say, we've got a vectorization like GPU or vectorization instruction sets.
Yes, exactly that. So you can just write one line and it will be evaluated at once. You can also vectorize this. I think there are some texts where it has been done, but it's easier to understand in this fashion how each node is being updated.
Okay, thanks.
Anand, I have one simple doubt.
Yes, Ankit.
Uh, could you go back to part number 2 of your code?
Yes.
ये जो L और C है, ये ट्रांसमिशन लाइन में,
Yes.
if you get back to part 2 of your the code.
I'm not sure why is it not updating. Just give me 1 second. It's stuck again.
Okay, don't worry.
Is it there?
Okay, fine. So the capacitance and inductance, does it actually change with this length? Is it the function of length?
You can make them as a function of length. So it will be one of the questions in assignment that you will get now. So once you have given this, yeah, I'm sorry.
At line number 39 and at line number 39 and 40, you make an array for capacitances 1 to cell something and L naught divide by Z. So what does it mean? It's array, it's a change.
So right now, this is the way we are. This is the way I usually define it. So instead of using LNC inside the update equation, so when you write the voltage value in terms of the new voltage value in terms of the old voltage value, and there is this delta T by C, delta Z, and then you have the current previous values of current. So you can either put the C values each at each point, or what I do is I put this as some coefficient. For example, what I've kept beta over here, and this beta is retaining that particular expression. And
No, so my doubt is either the C is variable or not. Is capacitance and inductance
over
is
here,
it variable over the length?
over here it is constant. I've assigned them as to be C naught, which is calculated from Z naught throughout these simulations, this particular space. So it is C naught throughout and L naught throughout. But what you can do is, since we have written it like this fashion, you can break this. For CL is basically rounding off this last point. So L naught is the total length. So this is the 0th position. This is the L naught position. And for the entire duration, for the entire length, I've kept them as C naught. But what you can do is break this down. What you can do is keep this as 0 to, for example, L naught by 2 distance as C1, and then keep L naught by 2 plus 1 node to the L naught final length as C2. So then you can have a transmission line which has C1 as the first part and then C2 as the next part. Then this way you can model in this particular code itself a cascaded transmission line.
Okay, thank you. Got it.
If you want to go more fancy, what you can do is keep instead of writing it like this, you can make this capacitance as a graded capacitance as well. So you can also vary the capacitance value throughout the length. So you can play along with this particular part of the code. Keep whatever capacitance value you want and inductance value you want, and see how your wave
Okay,
reacts.
you published a paper having this different capacitance, no, Anand?
Yeah, so
Variable capacitance.
in that case, the capacitance was a function of time. But yeah, so you can also do this with as a function of space as well. So which is more realistic. For example, if you want to model a transmission line having Z naught, and then Z1, Z2, Z3, and then there is a source over here, and then there is a load over here as ZL and R naught. So you can do this inside this code. You just need to put capacitance values at different C0, L0 values, C1, L1 values. You can do this inside this code itself.
Okay, thank you, Anand. Thank you so much.
Okay. Any further questions, Ankit, if you or anybody else, if you have any other questions?
No. From my side, there is no question.
Okay. Okay, so we'll just in part two, we defined the transmission lines characteristics. In the part three, we had the update equations. I'm not sure why this is not updating. Okay. Yeah. In part three, we saw the update equations, and the part 4 is where we just do the plot stuff. So this is nothing much. What we have done is we are storing the vz value, like we are using the vz value. This is the in MATLAB, the plot thing is like x value, y value, and then you can get fancy and add colors and stuff. Okay, why is this changing? Yeah, so the x value is basically the if this is your simulation space. Your x value is basically the length of the transmission line, and the v value throughout the simulation space is basically giving you the voltage value at each instant will show you one particular picture at one time instant. And since this entire plot code is inside the for loop, this particular plot thing updates at every time instant, and you see your Gaussian pulse moving forward. So this is not FDTD, but I'm explaining this because this will be in the code which I'll share. Again, this frame right video is part of the how exporting the videos which I included in the code. And this close right object is used and along with the file, so for writing the video file. So this is for the plotting, and this is for saving the video. So since I'll be sharing the MATLAB code, I'll suggest go through the text which we covered for the update equations, and regarding if you find any the functions which are related to MATLAB, just Google them. You'll get to know how each function works. For example, if you want to know what this grid frame is, what write video is, what line width is, or how plot works, if you are not familiar with MATLAB, so these things you can just read the MATLAB help library. So this was all for the code. Uh, and for the assignment, I'll be sharing the MATLAB code, the FDTD code for this lossless transmission line. I request you to run it for different Gaussian pulses, sinusoid, get familiar with the excitation, run it for different source resistance, characteristic impedance, and load resistance values. I showed you for R not equal to uh, source RS equal to Z naught equals to ZL values, and RS equals to Z naught not equals to ZL values. The third case, what you can try is rs not equal to z not equal to zl values. In this case, what you'll see is that your source faces some reflections at the beginning, then your wave travels, you'll see some reflections at this point also, and then when the wave returns back, there will be some reflection at the first boundary itself. So if you run it for a longer duration, you will see multiple reflections happening within this thing. To see the reflections more clearly, I'll suggest use Gaussian pulse, because if you use a sinusoidal pulse, once you start getting reflections from this particular point, that will just you'll see sine waves amplitude going up and down. So Gaussian pulse will help you see the reflections better. Then we have already discussed as on the from Ankit's question, uh, how to model cascaded transmission lines. So inside the code, there is this variable capacitance and inductance. Right now the code which I've given you, they will have the value from 1 to ZDIM as C0 and 1 to ZDIM as L0. What you can do is break this array into smaller parts, put different capacitance and inductance values, and then you can model uh, transmission line, cascaded transmission line of different impedances. For example, 50 ohm, 20 ohm, 10 ohm, something like that. And if you are able to implement this, you will be essentially implementing a filter. So this is what I expect everybody to run the code and see for different variables. For the Quran factor, we'll study in the next class. So I'll stop here. I'll take questions if you have.
आनंद, S parameters कब हम करेंगे? S parameters.
Yeah, so we'll discuss the S parameters in the next class, how we extract them.
Or how many classes we are now having in this next few weeks total?
The total, I'm expecting to conduct 5 classes, which is what I need to do before my review. We have already done 3. S parameters will be, I think, in the next class, and then we'll model lumped components on transmission line, which will be the 5th class. If we still have time, like I'll see if I can take a 6th class as well for these CRLS transmission lines, but I think we might not have enough time for that. Maybe in the next course which I offer, I'll try to cover that.
Okay.
So, Prof,
Thank
will
you.
you cover the case of 2D and 3D?
I could not follow you, Benjamin. Can you please repeat?
Will you cover the case of 2D and 3D solvers?
So since we are working with transmission lines in this particular course, which are a specialized case of Maxwell's equations in just one dimension. So the telegrapher's equations will be limited to one dimension. So in this course, we won't be doing that. But I've already taken a course which had covered 1D and 2D and the theory for 3D. I've not shared the codes for 3D in that course. I think I had shared the playlist in the group. I'll share it again. In that course, we work with Maxwell's equations with electric and magnetic fields, and we have covered 2D properly in that course, T and TM cases. So maybe you can take a look at that. I'll maybe in this year I call for my teaching requirements. I might offer the previous course along with this course together again, but I'm not still confirmed on that. If I do, I'll again float a course, and you, know, you can follow me on LinkedIn to be updated with that maybe.
Yeah.
Yeah,
Thank
one
you,
more
Prof.
question actually. That how do we extract the surface impedance of a unit cell when we take 2D case? Do you cover that part also?
Um, so your question is extraction of surface current
Impedance,
on the 2D
surface
case,
impedance. Yes, yes.
surface impedance. Um, I don't think we cover that. So the course is pretty basic for the question which you asked. Over there, we assign the impedance value and then see the wave reflected and transmitted wave. So your question is more on an inverse problem in which you see the scattered wave and then extract the impedance. Uh,
Yes, yes.
so maybe there's a course by Professor Uday Khonkoje in NPTEL. Maybe you can try looking into that. That's a pretty extensive CM course. He covers different methods as well. I don't perfectly recall if this particular thing was covered, but maybe it could be there.
Okay, thank you.
Okay, any
Thank
more
you.
questions before we
Uh,
conclude? Yeah.
Prof, can you please share with us on the WhatsApp group your LinkedIn profile so we can follow you and be able to know when you are doing the next course, please?
Sure. Yeah, I'll do that as well.
All right. Thank you. Thank you so much. Thank you for the lecture.
Yeah, thanks for joining. If we do not have any more questions, we can end the class for today. I don't think I'll be able to take any class on the coming Monday, or about Wednesday, I'll update on the group.
Okay. Thank you. Bye-bye.